Hello, today's video is going to be on the metric system. It's a system that utilizes powers of 10, and there are 7 elements in the metric system, and we're going to talk about the first 4. The others are not relevant to this particular experiment, but they'll be covered in subsequent videos and in lecture. First thing is that we have to define length. So what is length? Well, originally it was something defined by kings and queens of England, and they had an ulna, which is from your foot up to your belt, and that was 3 feet. And then they had barleycorns that were 3 of those defined an inch, and then they had a king's foot and so on. So a lot of these ancient measurements were not very precise. However, in ancient times, they did record what they used, and this was the pyramid in Giza. I had the good fortune to go with my friend Sammy 10 years ago, and we visited the pyramid. It was recorded as a height in cubits. So what's a cubit? Well, it's this measurement. This is an ancient measurement. It's from your elbow to the fingertip. And so the cubit was used to measure the pyramid, and also Noah's Ark. Noah's Ark was in the Bible, and the Bible records how big the ark was going to be according to the information there for Noah. His instructions were to make it 300 cubits long, 50 cubits wide, and 30 cubits tall. So by modern measurements, this thing would be the size of a football field. So it would be a very big ship, a big project for Mr. Noah. Now, some of these measurements were, of course, difficult to standardize. There were all kinds of competing definitions. There were several kinds of pounds. The libra was a Roman pound, and we still use the abbreviation LB for a libra. But there were wool pounds and English pounds, all kinds of different mass measurements. So the French decided in what was the date? 1793, the French decided that this was crazy, that we had to get rid of 3 feet to a yard and 12 to a dozen and all these funny measurements. The kings and queens have decided 5,280 feet to a mile, and these are very difficult to remember, all these things, and some of the things were kind of nonsensical. And some of them didn't even have a dimension, you know, like the fathom was that far and didn't have an actual dimension. So what the French did is they decided to measure the earth itself. Here's something that you could depend on. It didn't depend on people's parts or grains of sand or any of this kind of thing. And so what they did is they went to the earth itself. Originally they wanted to go from the North Pole to the equator, but that was kind of a difficult trip. So they said, well, okay, let's take 1/4 of the circumference. So they went from Barcelona to Dunkirk, and that defined the meter, divided by 10 to the 7th. So here's the original document. This will be in your video in better form for you to read. But the whole idea is that they then defined this meter to be a size that was very comparable to the yard, 39 inches versus 36. So it was well accepted by the general public. So that defined length pretty much. The next thing was, how about mass? Well, they had all these different things for mass. They had stones in Scotland. They had grains of wheat in Europe. They used all number of varying and competing dimensions. So what happened was, now that we had the dimension figured out with the meter, the idea was, let's use that to define mass. So what they did is that, okay, let's have 1 centimeter by 1 centimeter by 1 centimeter cube, fill it with water, and that'll be 1 gram. So now we have both mass and length defined by the meter. Now it turns out that after the meter had been defined this way, people said, well, how do I get a copy? I'm in the US, and the original was in France. They had a bar of platinum iridium and scribe with the marks that made it 1 meter. But if I wanted to have a copy of that, I have to bring my own reference and make a copy, and then make a copy of a copy, and so on. So there were errors that creep in. Well, it turns out that the interferometer, the light interferometer, was invented, and that was subsequently used to define the meter by wavelengths of light. So now it's 1.6 million and some other numbers, wavelengths of light defines a meter. So now anybody can do it. You don't need to go measure the Earth again. All you have to do is have a source of light and an interferometer, and you too can measure the meter with superb accuracy down to a nanometer. Next thing we'll talk about briefly is temperature. There were several scales of temperature defined. Daniel Fahrenheit came up with his first one, and that was in, 1724. And so he had an odd system of measurement. He had the inside of a horse's mouth, so-called. We don't know for sure if that's how he did it, but that was 100 degrees. And a mixture of ice and salt was 0. And that made water boil at 212. So these funny numbers were indicated in his system, and the question was why. And he wanted the difference between the human body at 96 and the freezing water at 32 to be 64, so you could divide by 2. It was 5 powers of 2. And I think the reason probably was making thermometers. You just keep cutting it in half and half and half and half. So it was probably a calibration thing. But it's inconvenient, and so Mr. Celsius, and that was in 1744, 20 years later, Mr. Celsius came up with a better one. He said, well, let's just use water. Water freezes at 0 and it boils at 100, that's it. So much simpler in concept, and so one wonders, and we use that pretty much universally today, except for the US, which still uses Fahrenheit. Why Fahrenheit? Well, because there's some handy features of Fahrenheit. 100 degrees is too hot to work, sort of thing. And so it's handy, and the degrees are somewhat smaller, so that you don't need to divide or have fractions as you would with centigrade. But these temperature scales had problems. One was, what do you do with negative numbers? It's hard to do math with negative values of temperature. The other problem is they're nonlinear. They're a little segment of temperature out of a huge expanse of possible temperatures. And so 2 degrees is not twice as hot as 1 degree in either system. So it turns out that the fix to that was from Lord Kelvin. And he came up with a scale. He said, well, let's have the absolute absence of temperature be 0. And then everything is nice and linear. So using that idea, he said, if I scale the temperatures like this, if I take the temperatures that I can measure and then extrapolate to 0, I wind up with absolute absence of temperature being minus 273 centigrade. So today, that's what we use, the Kelvin scale. So in the lab, we just take the centigrade, we add 273, and that's the absolute value. And this is linear, it's proportional, and we use it in all measurements, especially gas laws, which require temperatures. So the next topic is in the metric system is time. Time wasn't changed. We didn't do anything in metric system to change time. And time goes back a long, long ways. The original definition, of course, depends on the rotation of the Earth and then the Earth circumnavigating the sun, and it's not an exact value. So we have to add a day every 4 years to make it come out right. Otherwise, Christmas would wind up in July. And so we do that. Also, the Earth is slowing down. So we have to add about a second a year to keep the clocks right. So that's about it for time. How do we get the hours? Well, it turns out that the Egyptians came up with the concept of an hour. They started out with 12. And that was inconvenient. That was daytime hours, because the night added some more time, and then it changed from season to season. So they said, okay, we'll make it 24. So that's how we got to 24 hours per day. And why 60 minutes to the hour? Well, that's the Babylonians. They loved 60s. So they said, okay, let's divide the hour into 60 pieces and we'll have a minute. And somebody said, gee, that's pretty good. But what happens if I want something shorter than that? Well, let's just divide by another 60. We'll call it the second minute. And eventually they dropped the word second, just called it a minute, and just called it a second. So that's how we got to those numbers. Now, the next thing that happened with time is Einstein came along in 1905. He says, well, wait a minute, time is not a constant anymore. It depends on how fast you're going. And so it turns out there's a concept called time dilation. And it works like this. Depending on how fast you're going, the clock on Earth is different from the clock in the fast-moving object. So you say, well, why do we care? Well, because if you don't make a correction, your GPS values will be all wrong. You'll wind up in a different town or something. So these little tiny corrections are very important in modern science. So we've covered pretty much the basic dimensions. And so now we'll talk a little bit about the metric prefixes. So we don't normally put lots of zeros. We like to have a handy unit. So instead of having a meter divided by 100, we just said, okay, let's call it a centimeter. And then we'll call it a millimeter, and we'll call it a nanometer. So you don't have to deal with all these zeros. And so that's what we do in most sciences. So here's a brief outline. There's more detail we can get into. I'll have it in the video. And one of the problems that we have is that the United States is still one of only about 3 countries that still deal primarily with the Old English system. So how do you convert between metric and English? Well, there's several things you can do. There's exact conversions. 2.54 centimeters is exactly by definition 1 inch. And there's several other things. 453 grams is 1 pound. So you can do these conversions, and I'll provide a chart in the video that gives you an example of conversions. And this one is from Chem 32A, where we look at the amount of salt it would take to kill you, or half the people anyway. So now we'll get into the experiment itself, today's topic. And so we're going to look at the basic metric dimensions. And we'll start out with my friend here, the skeleton. And we'll measure the length of an object. And this is a femur. Everybody's got one, actually got 2, one on each leg. And so the experiment will be, you will sit down on a chair, and at home, you can do this, and you'll measure 2 things. You'll measure your height. So I'll measure my height, and then I'll measure my femur, which is from the hip out to the knee, and that'll be a value that is about 1/4 of my height. So what'll happen is when we look at the data, here's the image we'll have in the video. Here's some data from a prior semester. And we had 4 people in this particular group, and the average is about 4. So what that means is your height is about 4 times that of your femur length. Now, why is that useful? Well, a lot of times archaeologists don't find a whole skeleton of a person, they just find a part. And if they find the femur, they can then estimate how tall the person might have been. So that's part of what we'll do in that experiment. Then we have an experiment on volume. So we're going to measure volume, and we have a couple of ways of doing that. One is to measure the sugar cube. Let's start out with that one. So here's a box of sugar cubes, and what we'll do is we'll measure the length of the sugar cube. We'll put on this black surface so it's easy to do. Can you see? So what we'll do is we'll measure this sugar cube, and it looks to be about 15 millimeters. And I could measure all 3 sides, but generally speaking, they're going to be the same. So I take the dimensions on the sugar cube, and then I can calculate the volume of that. And so your data sheet in the report will look like this. And you'll enter the value for the length, width, and height. You calculate the volume. It's just a multiplication of the three. And then you divide by 1,000. Why 1,000? Well, because a millimeter is 1/10 of a centimeter. And we always express volumes in centimeters in chemistry. So you have 3 powers of 10, so it's 1,000. So you'll then write down the amount in cubic centimeters. Now what we can also do, that's volume, we'll also measure the volume of these little cups of cream. These little guys are typically served in restaurants and in bars and places. And so the question is, how accurate is the measurement of this cream cup? They tell you in the literature it's 0.375 of an ounce. So we're going to have to convert ounces to milliliters. But what we'll do is we'll open this little guy up and we'll pour it into a graduated cylinder. Make sure we got it all. So you have your measurement and you have the data from the manufacturer. So what you can do is compare, and how close did I come to his data. Next thing we'll do is we'll look at mass. We'll take a look at water. So here's a scale. You can see the temperature hopefully, and we'll put on this beaker, and I'll fill this grad cylinder to 100 mLs of water. I use this little squirt bottle to make an adjustment. We want it just exactly at 100. Okay, there it is. So here's 100 ml of water, and we're going to pour it into this beaker, and we're going to see what it weighs. And it looks like it says 98.85. What happened? I thought 1 cubic centimeter of water was supposed to be 1 gram. Why is it less than that? Well, the reason is temperature. It turns out that the definition of water being 1 gram per cubic centimeter is only at 4 degrees centigrade. That's where it's maximum density. So they wanted a stable value. So this is not at 4 degrees. This is room temperature, about 25 degrees. So if you look at the chart, we're over in here somewhere. And so actually the measurement is correct. And in the experiment, we'll provide you with a chart. So you can take your data and correct it for the temperature and see how close you come to the theoretical value. Now we'll also, set to 0 again, we'll also measure a sugar cube. We'll measure the mass. So this one says it's 3.59, about 3.6 grams. And so the manufacturer, what does he say? Well, the manufacturer, here's the data. This is a 1 pound box. And turns out there's 453 grams in a pound, and there's 126 cubes. So you do the division, and you get about the same number. So it turns out that we've validated the measurement that with our measurement we've validated what the box says. Now you got to be careful because the box also, when you look at the side panel, it says it's 4 grams. Well, wait a minute, that's not 3.6. They've rounded it up. So you got to be careful when you look at manufacturers' data. They tend to be generous with their own numbers. So now we're going to take a look at density. We measured this 100 ml of water, and we got about 100 grams. So that was the density of water. And there'll be a data sheet in your lab report that lets you put that data in. And then also we're going to do something a little different. We're going to take a solid object. Where's my solid object? Here it is. And I guess we can use the milk, why not? So we'll fill this grad cylinder about half full. I'll fill it to about 17. So I've got a 17 ml. Now it turns out Mr. Archimedes first observed this. He said if I put a solid object into liquid, it'll displace a certain amount equal to its volume. So we'll slide this guy in. So what used to be 17 milliliters is now something else. A little hard to read. I'll give you the data in the lab report. But the difference from 17 to this value is the volume of that particular object. Now we knew the weight, and now we know the volume, so we can figure out what the density is. In this particular example, the density was 2.9, and so using that information, we can estimate what it was. Here's a table of different things. 2.7 is aluminum, so it's pretty close to aluminum, so it was probably a piece of aluminum, but it could have been these other things. So when we give you the data in the experiment, you'll do your own calculation and decide what material it is. And then part E, this one is temperature, and in this case, I should have gotten a thermometer, but the point is what we'll do is with a thermometer, we'll measure the temperature of ice water, and that's easy to do. You just put some ice in a glass and stir it up. The object is not so much the measurement, but it's the conversion. So what we're going to do is take a measurement in either Fahrenheit or centigrade and then convert to the other system. And so there's rules about how you do that. You have to first of all get rid of the 32-degree offset, and then there's a 5/9 ratio between the size of the degrees. And so the little formula here that'll be provided gives you a way to do that. I think we're almost done. So one of the questions is, why are we still fooling around with inches when metric is so much better? And the answer is, it costs money. So here's a little cartoon showing people resisting change. And you would resist change largely because it costs something. You'd have to change your machinery. You'd have to change the way you measure stuff. It's already happening. We now buy wine in 750 ml bottles, and Coca-Cola comes in a 2-liter jug. And cars are mostly metric today. I've got an old Ford Explorer that's half metric and half English. The body was made here, and the engine and transmission were made in Asia. So I have to have 2 sets of tools, metric and English. But we're slowly migrating towards the metric system to be compatible with the rest of the world. I think that's all I had for today's experiment. So I hope you will enjoy it, and please take a look at the text document which comes along with the video. The text document will have all the data for you to use and the calculation sheets for you to use, plus additional information that's useful but wasn't really relevant to this particular experiment. Things like accuracy, precision, rounding, those kinds of things. So I'll see you next video.